Hello and welcome to Week 11, Part 1 of EGM310, Band Combinations. In this lesson, we will learn about how we can use different band combinations to highlight different land cover types in multispectral satellite images. In the rest of the lessons this week, we'll cover how we can use software to enhance images, making them easier to interpret. We'll talk about the elements of visual interpretation, how we can transform images to make them easier to interpret, and finally, we'll talk about different classification methods and how we can assess the accuracy of our classifications. We can view remotely sensed images as either single-band grayscale images or as multi-band composites. As you've seen in the practicals so far, composite images can help to highlight different features and aid in visual analysis. In this lesson, we're going to look at Landsat 8 OLI images in a number of different band combinations to see how these band combinations highlight different areas or features. You can use this presentation as a guide for your own work, such as in the TRS assignment, but feel free to try out your own combinations as well. We'll start with a grayscale image of OLI Band 5, the near-infrared band. Of course, you've seen this before when we looked at spectral properties. In the upper right panel here, we have our spectral signatures for different objects with the band highlighted as a vertical gray bar. Underneath that, I've also included a table which shows the different band names, the band numbers, and the bandwidth or wavelength range. So here, we're looking at light between 850 and 880 nanometers in the near-infrared. As we noted in Week 9, healthy chlorophyll-producing vegetation is quite bright in this wavelength range. It reflects quite highly, while water is nearly black owing to its near total absorption of near-infrared wavelengths. Another image that we've seen before, this is a true color composite with the red wavelengths recorded by the sensor displayed as red on the computer screen, green wavelengths displayed as green, and blue wavelengths displayed as blue. You can see lots of green in the image. Most of the different agricultural crops in the region reflect more strongly in visible green and blue than they do in the red. Cities and urban areas are gray. Shallow water appears blue to green, depending on the depth and the sediments in the water. In the false color infrared vegetation image, the near infrared recorded by the sensor is displayed as red on the computer screen. The red wavelengths are displayed as green, and green wavelengths are displayed as blue. As we noted last time that we looked at this, everything looks red now, owing to much stronger reflection of vegetation in the near infrared than in the visible wavelengths. We can also see that the water appears very dark, mostly black, with some hints of blue or green. Again, because the water reflects very little in the near-infrared. In this color combination, urban areas appear mostly blue and gray, indicating that they're fairly bright across the three bands, but perhaps a little bit higher in the green wavelengths. This color combination uses the shortwave infrared band 2, which is Landsat band 7, around 2200 nanometers in the red channel, the shortwave infrared band 1, which is around 1600 nanometers in the green channel, and the visible red band in the blue channel. In this combination, we can see that the vegetated areas are still mostly green. Again, most healthy chlorophyll-producing plants reflect more at about 1600 nanometers than at 2200 nanometers or in the visible red wavelengths. We can also see the different urban or built-up areas in a sort of purple color. This contrast, the purple with the green vegetation, is what helps make this a useful combination for visually identifying urban areas. Additionally, the use of longer wavelengths helps reduce the influence of atmospheric pollution, such as smog or smoke. Remember that Mie scattering depends on the wavelength, and as we increase the wavelength, the amount of scattering goes down. So this is especially helpful in urban areas where we have pollution. Next up, we have a false color composite that is useful for monitoring agriculture. So this is a combination of the shortwave infrared around 1600 nanometers for the red channel, the near infrared for the green channel, and the visible blue for the blue channel. In this composite, most healthy vegetation appears bright green. Bare earth is sort of a pink or magenta color. So we can see that there are some fields that very clearly have a lot of growing happening. We have other fields where we don't have plants growing, or at least not to the same height or the same density. You can see that, again, the urban areas are a deep purple, which helps to distinguish them from vegetation as well. This false color composite is useful for minimizing a number of atmospheric effects. It uses both shortwave infrared bands and the near infrared band, all of which have longer wavelengths. As we saw with the urban false color composite, both Rayleigh scattering and Mies scattering occur when the wavelength of the electromagnetic radiation is small relative to the size of the scattering particle. Most particles in the atmosphere, things like smoke, smog, dust particles, are much smaller than the wavelengths that we detect in these bands, meaning there's very little atmospheric scattering that occurs. Thus, the picture is typically much sharper than the false color composites using shorter wavelengths. This color combination can also be useful for geologic mapping, as certain minerals can be easier to discern using this particular band combination. A combination of the near infrared band in the red channel, the shortwave infrared band 1 in the green channel, and the visible red band in the blue channel provides a better definition of land and water boundaries, especially for inland lakes and streams. Water appears almost entirely black in this color combination, while most other surfaces are shades of green, blue, or orange. This color combination can also be used to map differences in soil moisture, as a lot of the differences that we see in various vegetation and soil covers are due to differences in water content. Wetter soil will appear darker in this color combination, while drier soil will appear brighter. This color combination is used to distinguish differences in bare earth, that is, land cover without significant vegetation. This is more difficult to see here because most of this image is covered by vegetation. It can also be used to distinguish cloud cover from snow and ice. Clouds appear bright across most all of these wavelengths, while snow and ice are especially bright in visible and near infrared wavelengths, and a sharp drop off to the shortwave infrared. In this band combination, snow and ice will appear blue and green, while clouds will still appear mostly white and gray. Once again, you can read more about the concepts that we've covered in this lesson in Chapter 4, Section 6 of Campbell and Wynne. I've also included some different links to more information on interpreting false color images, including a page where you can try your own color combinations. Finally, I've relinked a video that talks about the different Landsat bands, as it covers some of the same material that we've discussed today. That's all for this lesson. I hope you found it interesting, and if you have any questions, please don't hesitate to email me or post in the discussion forum on Blackboard. Bye!